So in this problem, a water tank develops a small hole and water runs out at 6 meters per second. And the question is, how far below the surface did the hole develop? And so this is a Bernoulli principle problem. Bernoulli's principle states that the pressure plus 1/2 rho v squared plus rho gh is a constant for the whole fluid. And so that means you can write this down for different points in the fluid, and they all have to be the same. And so, for example, I could pick this is point 2, and this is point 1, just right at the surface. And I could say, look, P1 plus 1/2 rho V1 squared plus rho g H1 equals P2 plus 1/2 rho V2 squared plus rho g H2. Can you see that? Maybe not. Kind of on now, I think. And so if I evaluate all these terms here and then evaluate them here, they have to be the same. Here is, just right outside the fluid, right? And so there are a couple things we can notice about this. First, P1 equals P2 equals the atmospheric pressure, right? This is outside the hole, and so it's a small hole, and so it's just atmospheric pressure there. Same thing with here at the top of the fluid, it's atmospheric pressure. And so I can cancel both of those in this because the pressures are the same. Also, I can say, look, V1, if it's a small hole, the water's not running out really fast, V1 is just 0. And so I end up with 3 terms here. I get rho g H1 equals 1/2 rho V2 squared plus rho g H2. Notice every term has a rho in it, and so I can cancel those. And I'm solving for this height, which h is equal to H1 minus H2. Right, that's the height I want. And so I can subtract these guys over, and I can say, look, GH1 minus GH2 equals 1/2 rho V2 squared. Or H1 minus H2 is equal to V squared, V2 squared over 2G. So H is equal to 6 meters per second squared over 2 times 10 meters per second squared. Right. That gives me H is equal to 1.8 meters. A piece of wood and a piece of iron of identical volume are thrown in a pool. The iron sinks to the bottom, and the wood floats. So this is the picture, right? Here's the wood, and here's the iron. And the question is, which experiences a greater buoyant force, right? So if you remember Archimedes' principle is the buoyant force equals the weight of the displaced water. Or really just the weight of the displaced fluid, right? Because it doesn't have to be water. Since they have the same volume, the iron is clearly displacing more fluid because some of the wood is sitting above the surface of the water. And so that says the iron The buoyant force acting on the iron is greater than the buoyant force acting on the wood. So in the spirit of that problem, what is the buoyant force on a 1 kilogram lump of iron submerged in water? Right, and so same story, right? Here's my lump of iron, and we say the buoyant force is equal to the weight of the displaced water. Well, what is the weight of the displaced water? Well, the weight of the displaced water is just the mass of the displaced water times gravity, right? Well, what's the mass of the displaced water? The mass of the displaced water is equal to the density of water times the volume of the iron, right? Because the volume of the piece of iron is what pushes the water out of the way and displaces it. And so the buoyant force is equal to the density of water times the volume of the iron times gravity. Well, what's the volume of the iron? Well, all we know is the mass of the iron, and so the volume of the iron comes from the equation that the density is equal to the mass divided by the volume. And that means the volume is equal to the mass of the iron times the density of the iron. So the buoyant force that we're talking about is equal to the density of water times the mass of the iron over the density of iron times gravity. And so we can write that this way: the density of water divided by the density of iron times the mass of the iron times gravity, right? And so the density of water is, so this is 1,000 kilograms per cubic meter. And this is 7,800, roughly, kilograms per cubic meter, times the mass of the iron is 1 kilogram, times gravity, which is, call it 10 meters per second squared. So that's 1 over 7.8, which is about 0.13 times 1 times 10, which is just times 10. It's about 1.3. These units cancel kilogram meters per second squared, or newtons. So that's my buoyant force. This might be better. In this problem, it says a hospital patient is fed intravenously with a liquid. So I'm going to draw a picture of this. Here's my hospital patient, right?
Yeah.
And then they've got a bag that's a certain height, 1.2 meters above the arm, and the density of the fluid is 1.09 1090. So the density is 1090 kilograms per meter cubed. Is that showing up okay?
If you'll move the camera up a little bit, I can't read the part on the top where the bag is. Yeah, there you go.
There we go. I wonder why it's, let me just pull that up for a second. It's weird. I don't know why it's oh. Oh, I see. The screen ends. All right. All right. So that's the situation. It says a hospital patient is fed intravenously with a liquid that's 1,090 kilograms per cubic meter. The bag is 1.2 meters above the patient's arm. What's the gauge pressure in Pascal exerted on his veins as the pressure enters? And so, so you can just say the gauge pressure is just rho times g times the height of the fluid, if you want to. So this is the pressure difference between the top of a fluid and the bottom of a fluid of height h.
Yeah.
So you could actually apply Bernoulli's principle here if you wanted to. You could say P1 plus 1/2 rho g h1 plus 1/2 rho v1 squared is equal to P2 plus rho g h2 plus 1/2 rho v2 squared. And since the velocities are really slow, you can just
Hey,
am I off the screen again?
Why on the left side is it 1/2 PGH?
It's not. It should be.
Okay.
Sorry. I usually put 1/2 rho v squared there, and I don't know, I shifted gears in the middle for some reason. Yeah, you're absolutely right. It's just 1/2. It's just P1 plus. Thank you for fixing that.
Yeah.
And so those two guys cancel, and what you get is P2 minus P1. In other words, if this was position, if this was position 2, the top is 1 and the bottom is 2, right? And so the pressure at the bottom minus the pressure at the top is rho g h1 minus rho g h2, which is the same thing we're saying up here. We're saying the gauge pressure, which is the pressure difference, is equal to rho g times the height difference. And those two say the same thing.
Yeah.
And so the pressure is just 1,090 kilograms per cubic meter times 10 meters per second squared times 1.2 meters. And so it's going to be around maybe 1,300 or something, 13,000, something like that. Yeah, 1.3 times 10 to the 4th. And it comes out as, so a meters cancel with 1 of meters makes that a 2. That cancels, makes it a 1. And so this is kilogram per meter second squared, but that's just Newton per meter squared. And that's a Pascal.
All right.
All right, you ready for the next one?
Yeah.
So this is planet X. Planet X has a radius of 3 times 10 to the 6 meters. 3 times 10 to the 6 meters. That's the radius. And the acceleration of gravity, g for x, is equal to 2.8 meters per second squared. I'll just scroll here. What is the mass in kilograms of planet X, right? And so if you remember, the force of gravity on the surface of the planet like Earth is just mg, but it's also equal to g mm over the radius of the planet squared.
Yeah.
where m was mass of the Earth, right? And that's g for the Earth. Well, it's the same thing on x. The mass of some object, like a ball on planet X, is just mg times m times g on x, and that's equal to g times the mass of x times the mass of the ball divided by the radius of x squared. And so I can cancel the m's. It doesn't matter what the object is. And the only thing I don't know here is the mass of x, right? And so if I solve for mx for here, I get it's gx times rx squared over big G. So I have to evaluate that, right? And I have to say, all right, it's 2.8 meters per second squared times 3 times 10 to the 6th squared divided by 6.67 times 10 to the negative 11th. So I get mx is equal to 2.8 meters per second squared. That's an 8. Times 3 times 10 to the 6th meters squared divided by 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And what I get for that is about 3.8 times 10 to the 23rd kilograms. Which looks like choice C on there.
Alrighty.
So a block has weight W on the surface of the Earth. So here's my block, right? And its weight, which is mg, is W, right? And the question is, if the Earth's mass were kept the same, but its radius was 1/3 its current size, what would the new weight of the block be? Do you have any? How would we get that? What's going to be different?
The force of gravity, isn't it?
Yeah, the acceleration of gravity, right? But the force as well.
Yeah. I meant the acceleration side.
Yeah, you're right, though. You can call it the force too, because and so we just said that mg is equal to g times the mass of the Earth times the mass of the block divided by the radius of the Earth squared. Well, if I make this radius of the Earth 3 times smaller, what happens to the whole quantity?
It gets way bigger.
Yeah, how much bigger?
Well, isn't it like 3 times bigger?
Well, but you're on it.
Well, if the denominator gets way smaller, or way smaller than
So how much smaller does the denominator get if the radius of the Earth is 3 times smaller and I'm squaring it?
1/3.
If I'm squaring it.
Oh, sorry.
That's all right.
I don't know. I feel like this is obvious, but the answer is not coming into my head.
That's all right. So I'm squaring this thing. And so when I square it, what's the value of the thing of the denominator?
So like 1/9?
Yeah.
No. Yeah, because you
so
third down
this
there.
becomes RE squared over 9, right? Denominator becomes the numerator, and so it's just 9 times g times the mass of the Earth times the mass of the block over the radius of the Earth squared, right? I go from here to here to here, right? That 9 just comes up. Well, this is back to this thing, right? GM, mass of the Earth times the mass of the object over the radius of the Earth squared is what we started with. And so the new thing is 9 times bigger. You with me?
Yeah.
And so it's equal to 9W, right? This is just mg, and so it's equal to 9 times mg, which is 9 times the weight. So you get this is a whole philosophy behind black holes, right? As you compress the mass, the gravitational, the acceleration of gravity gets larger much faster than just than just the reduction of the size. It goes as a square of the reduction of size. Make it a third as big, gravity gets 9 times bigger. You make it 100 times smaller, the gravity gets 10,000 times larger. And that's why stuff on compact objects can't get away. All right, so this is a tides question, number 7. It says you're lying on a beach and the sun is setting in the western horizon and the full moon is rising in the east. This special alignment of the sun, earth, and moon gives rise to what kind of tides? This is, you just have to know. So I'll just do a brief thing about tides, right? Here's the Earth. Most of the tides due to the Earth are caused by the moon, right? And the moon pulls harder on the near side of the Earth than it does on the far side of the Earth. And so the water gets pulled harder on this side and less hard on this side. So this stuff gets left behind a little bit and this stuff gets pulled forward a little bit. And you're left with an Earth that looks stretched this way. Right? And if the Earth, the moon, and the sun make a line, then the sun makes that worse. And that's called a spring tide. And it turns out it doesn't matter which side the sun is on. If the Earth, moon, and the sun make a line, which is what this is describing, you get an extra stretchy Earth, or an extra stretched Earth, which gives rise to what they call spring tides. And the reason they call them spring tides, it happens, every 2 weeks. The moon goes around the Earth once a month. And so about every 2 weeks, it's either on the opposite side from the sun or the near side from the sun. And those are, and all that means is that the Earth's tides are extra big. And when you're let's say you're on this part of the Earth, right? Then when the Earth rotates around, I don't know which way it's rotating, let's say it's rotating, 6 hours from now, you get a huge tide. And so they would spring up, the tide would spring up, they would call them spring tides. And so when they make a 90-degree angle, the other question you could ask is, it's noon and the moon's on the horizon, so the sun's overhead, the moon's on the horizon. These are reduced because the sun's trying to stretch the Earth this way and the moon's trying to stretch the Earth, and they kind of cancel each other out. And those are called neap tides. And those are lower than normal tides. And those also happen every 2 weeks. And so you get a spring tide, then you get a neap tide, then a spring tide, then a neap tide. All right, that was one of Newton's big contributions, because they understood tides and they had tide tables, but they didn't know why it happened. And Newton explained it with gravity. All right, so that was 7. What is the pressure and it's saying the mass of the elephant is equal to 5050 kilograms. The area of a foot is 430 centimeters squared. Right. And so what's the relationship among these things? Do you know?
Well, it's just the mass, or the mass is exerted, or the weight is exerted through a certain area.
Yep.
Basically.
Yep, that's right. And so the pressure is the force over the area. And the force in this case, just as you said, is the weight. And so it's mg over the area. And the only catch is we're asking about 1 foot. And so it's the mass of the elephant over 4 is the weight it's the mass we're talking about, times gravity over the area. And so that's 5050 kilograms over 4 times 10 meters per second squared. And I have to be a little careful with this area, right? If I want to convert that into square meters so that I have the right, so I have SI units all the way through, I have to multiply it by a meter over 100 centimeters, but I have to square it because I've got centimeters squared. And so I'm dividing this by 10,000. 1, 2, 3, 1, 2, 3. And so that's equal to 0.043 meters squared. I'm going to say that's 1260 kilograms times 10 meters per second squared divided by 0.43. That's going to be about 300. It's going to be 10,000 times 2.5, maybe 25,000. I'm going to work it out. Oh, it's not point. It's 0.043, and it's meters squared. What I get for this is 2.9 times 10 to the 5th. Pascals. And so for this one, it's none of the above. For the choice.
All right.
Oh, no, wait a minute. I was reading the wrong solutions. It's choice B, right? 2.9, sorry, 2.9 is choice B. It has it right on there. 2.9 times 10 to the 5th pascals.
All right.
A satellite orbits the moon in a circular orbit. So here's the moon in a circular orbit. So here's my satellite. Its speed is 1,500 meters per second. What is the distance of the satellite from the moon? From the center of the moon, r equals question mark. Right. And so do you remember this? So if the thing's moving in a circle, what kind of acceleration does it have?
Oh, shoot.
It's all right.
It's like on the tip of my tongue.
Yep. So do you remember the formula for it? We call this centripetal acceleration. It's equal to,
Oh,
yeah, we haven't talked about this in a month.
yeah, it's been a while. I forgot, kind of.
Squared over r.
Yes. Yeah.
And so the force acting on it, what force is pulling on the satellite? What's causing the satellite to stay in orbit?
Oh, the gravity of the moon.
Yep. And so what we have here is the sum of the forces is equal to the mass times the acceleration, like we always do. And we just got one force here. That's just g times the mass of the moon times the mass of the satellite divided by r squared is equal to m times v squared over r. And so I can cancel out the masses, and all I'm left with is the mass of the moon there, right? And so I can cancel one of the r's, and I get g times the mass of the moon over the orbital radius is equal to v squared, or r is equal to g times the mass of the moon over v squared. And that's equal to 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. See if I can pull up the mass of the moon. I think it's like 7.35 times 10 to the 22nd kilograms. I'm pretty sure that's right. And then this is the velocity is 1,500 meters per second, all squared. I get 2.17 times 10 to the 6th meters, which is choice A on there.
What did you say, 2.17?
That's what I got.
Okay. Times 10 to the negative 6?
Times 10 to the positive 6.
Oh, okay, sorry.
Can you see that okay on there?
It's down below.
Oh.
Where
Dang it.
all I'm down to is, yeah, there you go.
Have I done the last couple of them like that?
No.
Okay.
Just
All right.
that part.
Good. All right.
Yeah, I've got all the work.
Okay. All right. So let's see if we can do the last one. And the last one is that the last one? Yep.
Yeah, 10.
And so this is almost the same drawing, right? This is almost the same problem. That's not a very good circle, but I'll just move my Earth, make it look better, right? Here's my satellite, right? And here's my R. And so we want to know the acceleration. So the sum of the forces equals the mass times the acceleration. That's just G times the mass of the Earth times the mass of the satellite divided by R squared is equal to MA. Cancel the M's, and I just get the acceleration is G times the mass of the Earth divided by R squared. Right? If this was on the surface of the Earth, that would just be 9.8. But it's not, it's going to be something less than that. And so it's not, but it's not too far. I'm going to guess it's the 8.4. But we've just got to multiply all these out, right? This is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. The Earth's mass is 6 times 10 to the 24th kilograms. And this is 8 times 10 to the 6 meters, all squared. And so what is that? That's going to be, I'll just do it, 6.67 e negative 11 times 6 e 24 divided by 8 e 6 squared. I was wrong. I get about 6.25 times 10 to the, meters per second squared, which is answer C. Oops, I'm off the screen again, aren't I? Wasn't too bad.
No, you're good.
All right. All right. Does that work?
Yeah, it was good. Thank you.
You bet. Maybe I should find some more example problems and throw them out there. Anyway, I'll post this maybe this afternoon and let other people look at it. I appreciate you going through it with me. All right, man.
Yeah, no problem. Is there going to be any other practice problems?
I don't know. Would you like some?
I'll take as much as I can get. I need it.
I'll see if I can put some up.
All right. Yeah. So you said you plan for half of it to be like the waves and the gravity and pressure, like the new stuff.
Yep.
And then half of it's going to be stuff we already covered.
Yep. And I'm just going to have a little bit on the waves. So most of the new stuff will just be the gravity and the pressure, because I don't feel like I've done any homework really with you on the waves, on the oscillations and waves. And so most of the new stuff will be gravity and pressure, and then the old stuff will just be the whole semester.
All right, cool.
All right, man. Have a great day.
Oh, you too. Thank you.
Yes, sir.